is huge. It can also be misunderstood. It often is. One of your next exam questions, I Googled last term, what is a p-value? And the first hit on Google has a wrong answer. And I'm going to have you guys go to that site, find the wrong answer, and correct it and make it right. Because it's one of those things that's so easy to misinterpret. Okay, this is just catch-up stuff. You guys have already talked about this. Caffeine significantly lowered compared to placebo. Okay, some words, you've probably heard them before. But just in case you haven't, you're going to have two groups in this study. And in this case, the two groups are actually the same 9 guys getting different dosages. And I think they're doing that because with 9, the margin of error is already very, very large. If you knock it down to 3, it's going to be even trickier.
Well, that's when they have 3 groups. They have the 1.5, 3,
and the 0,
so
placebo.
3.
So if you try to break it down, I mean, yes, but you can also just give all 9 the test each time and assure that the liver is flushing all the caffeine out between. That's one way of doing it. Ideally, you don't want to do that because you want to erase any residual doubt about the drug being in the system and carrying over from trial to trial. But if you wait long enough, your liver being affected is, well, of course those guys do a lot of EPO. Your liver's might be like Swiss cheese. It's possible. But yes, the idea is you've controlled for it. So you've got an experimental group. Those are the guys that are getting, whatever you're testing, in this case caffeine. And you've got the control group, which are the ones that are getting the placebo, and you're trying to compare them. And they are, as Deanne pointed out with plants, identical in every way except for that. The idea, and this is obviously ideal. It's idealized, right? Because can you control for every single difference? Not unless you're breeding stormtroopers from Star Wars. They have Jango Fett, you're making a whole bunch of clones of Jango Fett. That's the only way you're going to get around from that, because people have different physiological differences. Right? They have different physiological things that you can't account for, which show up sometimes in later studies, like, oh my god, we forgot to check the tire pressure. And the Ford's tire pressure, remember that one? We forgot to check the damn tire pressure, the damn Buick had higher tire pressure than the other ones, and that one had better mileage. We thought it was the engine, it was actually the tires. And that's one of those things, sometimes variables slip by that you miss. So it's important to catch all the ones you can, and this is also why it's important to have other folks replicate, because they might creatively think of something else that you didn't. Very important, very important. All right, now, I mentioned this before. You want to see the unexpected. But in order to experience the true unexpected nature of that, if it is truly unexpected, it's only unexpected when you compare it to the null. It has to be different from what you're expecting. So what you do is, you just go into it assuming the expected, and prepare to hopefully be surprised by the unexpected when it happens. So, assuming the null. You're going to go in assuming that the null is true, and hopefully find some data that shows that it doesn't look like it's true. Is that fair? We'll come back to it with a graphic soon, which I think will hammer that point home. Okay, now, Renee, your awesome question. These p-values. What are these p? Now, somebody mentioned, I think it was Tim last class, there's a lot of damn p's in statistics. There are. Lots and lots of that letter P. There's capital P, lowercase p, p hat, p bar, p tilde. This is capital P. We're going to use him, I'm going to always call him capital P. Your textbook does not, on any assessment I use a P value, it'll be a capital P. Sometimes I'll make it like 28-point font to really make it stand out. The idea of the P value is it's a conditional probability. And here's the deal. What do you remember about conditional probabilities? We got away from these towards the end of 243 because things were independent. We started treating things as independent at the end of 243. What do you remember about conditionals? The slash in the middle. What do you remember about it? Say that again, right? Oh, that's how you deal with combining probabilities. Thank you. You're one step beyond me right now. Thank you. We'll come back to that as well. Harrison, go.
It separates it into a fraction, so it's the null hypothesis is true out of your total. So it's like the percent chance that that's going to be, right?
It's been too long. This is what I was worried about. I was worried about this. It's not a fraction.
No,
it's not a fraction.
Of probability?
I mean, well, probabilities are fractions, but that's not what that bar means.
So it's a yield, isn't it? So like you get out of the data that you have, you're specifically looking at the hypothesis that was true.
I'm glad I asked this question. One of those two statements is the assumption, and one of those two statements is what you're testing with your data. Which one is the one you're assuming?
Second.
that the null hypothesis is true. So what's after the bar is what you're going in assuming. Is what you're going in assuming.
So it's that given.
That's what this guy means. It means given, and that's something we have not talked about in weeks. It's been months. We're going to call it months because it's probably last October. So assuming or given that the null hypothesis is true, what's the chance that we got the data that we did? That's what a p-value is. So you see when we said assuming the null, that's right here. That's right here in that second part. Assuming the null is true, what's the chance that we got data that we did? So what we're going to be looking at in all of these bike cyclists' caffeine heart rate articles, what's the chance, assuming caffeine had no effect, lowering, what's the chance we actually got lower data? Because that's what we're looking for. We're trying to be surprised. We're trying to be the recipients of an unexpected result. So we want to see lowered heart rate while we're not expecting it. Remember the contradiction we spoke of last class? We're looking for a contradiction. We're looking to be surprised. We're looking to expect the normal heart rates with caffeine, and boom, surprise! Guess what? It actually dropped. That's what we want. That's what we want, and this measurement will tell us if we can believe it or not. We haven't gotten into how to calculate that measure yet, which is what today's all about. Actually, it's not what today's all about, it's what Wednesday's all about. Today's just about being given those numbers and processing. Gesundheit, ask me questions right now about that. Skylar, go. What are you thinking? What are you thinking? Go.
So that's 5%, right?
Mm-hmm. Hold that thought for like 2 minutes. Yes, this is what we're going to be comparing to 5%. And some of you might be thinking, what the hell is 5%? We're going to come back to a graph, which hopefully will clear this up. But yes, Skylar, yes, this number, good, Sherry, this number will be compared to a 5%, somewhat arbitrarily, but that's the usual baseline. Harrison, go. What do you got? What do you got?
95% of your data is within 2 standard deviations.
You got it. You've made the connection. You guys have made the connection between the old and the new. Here's the deal. Okay. P is less than 5%. This is the next little graphic on your sheet there. I'm going to start again. Sorry, it's not in color on yours.